And Quantas is like where we do a post PEX analysis. And Ashura is also like for LVS and DRC and extraction. That is from the Mentor graphics. So how the tool works is it is like a common platform where multiple parties will give their plugins. So let's say Cadence is uh, a bigger tool, and it does schematic editor, but for extraction, like extend extend. So we want to do an extraction from the layout, parasitics and everything. So the Mentor graphics Ashura provides a better match, better close result. So we can get the Ashura from the Mentor graphics and implement that in the Cadence. So that is how it works. So many plugins will be there. So mostly it is based on number of licenses. So schematic editor takes one license. So we purchase license from the vendor in terms of let's say in terms of monthly or yearly or 6 months on the renewal. So it is more like a top up kind of thing. So we get like a card based thing. So that is how the so each simulation. Let's say you want one single schematic license to to work on the schematic editor. So to get the license, we need to purchase from the cadence. So that is how it is there. And this is how the schematic editor looks like, the cadence schematic editor in the industry, what we do. So this is one of the circuit which I have worked on. So this looks like, I would say, um, here you can edit in the transistor level, and we there is a symbol which you may see like an op amp symbol. So that is an hierarchy. So we can build multiple hierarchies as a schematic, and we can go inside. So to simplify, let's say you have 200 transistor in a design. It is very difficult to place all the 200 in one single page. So what we do is we will categorize each. So this op-amp symbol has some 10 or 20 transistors inside. So we symbolize it. So this makes the schematic readable and more intuitive to learn. So that this is the um, schematic editor where we have all kind of editing wires, and we can place the MOSFET. So these MOSFETs are from the foundry. So they will give you the model file. So this is how the schematic editor looks like, and this is the layout Excel. Excel is the name given for various features. Earlier it used to be a layout L. Now it is Excel, meaning they are giving more features to it. Meaning, so you have a schematic like this, and you want to have the same devices in the Excel. Excel is like a different window. We'll open a different window where we want to import um, all the MOSFETs and all the connections. So that is being done by the layout engineer. So this tool. So here we will import all the transistors from that. So that requires a connection between the schematic and the layout, so that it implements all the MOSFETs and the resistor, capacitor, all the devices. So connections, it will um show you the connections from the schematic. So it takes, for example, in this picture, you have the left side, you have one MOSFET, left bottom, and there is the gate of the two MOSFETs are connected. So that connection will be directed to the layout. So it will tell you this device gate has to be connected to that device. So that we will check by the LVS, the layout versus schematic tool. So that will check all the cross connections. So this is the layout tool looks like. So here we have multiple devices and multiple layers. So we develop ICs with the multiple layers. Say um, the number of metals. So if you could take an example of a PCB design, so you have multiple layers of a routing. The device will be on one layer, but all routings will take, let's say, till 7 layers, 10-layer board. Similarly, in ICs, all the connections cannot be done with one single layer. in the layout particularly. So each device will stay in the bottom layer, which is called the base layer, and routings will be routings, meaning the connections between the each devices, and all the left side, all yellow colors are the pads. So all the connections are being done with the multiple layers. So here, if you could see all different colors in the routing. Routing here is all the square shaped thing at the end. So it crosses each other. So you cannot route each line in between. So it requires multiple layers. So that is been done in the layout Excel tool. So this is the tool. This is how the tool looks like, the Cadence layout tool. And this is the ADL, analog design environment. So what we do here is, these are the parameters we give in the schematic. Let's say W1, W2 are the width of the transistor, V bias is the bias voltage, and L is the length, the IB is the current. So here we specify all the numbers. The schematic we provide this instead of giving 500 millivolt in the schematic, we give the name as a general name as a V bias. So this 500 millivolt we can provide it here. So this analysis section is all what is required. So here we have a DC analysis, AC analysis, and transient analysis. So DC is for checking all the operating points. AC is for checking the bandwidth of the circuit and also the stability. And the transient is to check the real time time domain analysis. So here outputs. Here we save all the outputs, and it will tell you what is the gain of the circuit, what is the gain bandwidth, what is the power of the circuit. It will calculate. So it is more of a handy tool. Comes with. And this is how the ADXL. So ADL and ADXL both are interlinked, but the use of this ADXL here is, in ADL you can do one simulation at a time, but here you can do multiple simulation parallelly. Also, you have a different kind of conditions in the chip. Uh, if you could remember, a die which is 12-inch and a chip inside is, let's say, very smaller in terms of micron. It's the tip of a pencil, right? So in that chip, there will be I mean, the 12-inch wafer. If if you take the chip from the center, that is called the typical. Okay, so if you go towards edge, and the performance of the MOSFET differs. Okay, that we call corners, meaning, let's say, um, for example, if you take a piece of a cake, you cut at the center, it will have all right, a white colored one inside. So if you take at the end, you get either cream or a baked one, right? So if you similarly in the wafer, if you take chip from the center, it gives the typical result. But if you go towards at the edge of the chip, so each wafer will have say 10,000 chips, right? Each around circular wafer. So if you take each from different places, each device behaves differently. That is the nature of that manufacturing process. So in this picture, if you could see in the top, you see SS, FS, and SF and the FF, right? So those are all like corners. SS meaning slow NMOS, slow PMOS, meaning so the device, the slow is based on the VT. So if the VT is high, it is slow device, and VT is low, it is fast device. So in a complete one wafer, all the transistor cannot be at the same VT. The VT will vary. Okay. So that is why we want to design for all the corners. For that is the use of this tool. So you can use multiple corners here and run and check what is the result at each different corners, so that you cover the whole wafer. So typically, if you design and if you send for the tape out or manufacturing, so the chips at the end will behave differently. So whenever we design the chip, we it is done with the all the corners, whether it is passing or not. So if you could see here, all the green colors. If you take the first line, current, so nominal is there, right? That is 7.13 milliampere. So that is a typical number. But if you see, if it is slow, it is 8.23 milliampere. and it is at fast. The last it is 8.037 milliampere. So this is how we could analyze whether the chip is passing the specification all the corners or not. So this is how the ADXL looks like, and how the simulation tool works. Okay, so the schematic is a GUI, okay, user interface. It's a graphical user interface where you place all the transistors in and connect. That is for our understanding. So what the tool does, it converts the schematic into a netlist. Netlist is a list of it's like a notepad, note text file where it writes all the connections for its understanding. That for us it is very difficult to understand because it will have some thousands of lines that we cannot do it. So that is why we do in terms of GUI, and it converts into a netlist. So and then it runs a specified simulation, whether transient, DC, or AC, and it dumps the output in a text or a Excel format. Okay, so everything is done in terms of text or numerical format. So what we see here is the GUI format, which is easily readable. So that is how the simulation tool works. So we give the input as a GUI, and background it generates the message and it runs the simulation, dumps the output. So when we want to see the result, we take it from the dumped file, and it converts into a GUI. So that is how a simulation tool works. So what are the requirements for a simulator? So if you want to run a simulation, what are the requirements? So the Foundry model file. Here, Foundry meaning there are very little number of foundries in the world. So namely, it is TSMC, Global Foundries, Samsung, Micron. So these are the very few we could name. There are others as well, else as well, but these are the major players in the foundry. So they will provide you the model file. So each transistor, how it behaves in different corners, they will provide you. That is called model file. So with that, we should be able to do all the simulation. And the input netlist. Input netlist is what it is. The schematic is being converted into a netlist, and define the variables. Variables is the ADL in the left section. I have showed you all the VDD and M1, all those things. So set up the environment. Environment is what temperature you want to run, a high temperature. So usually the chip is checked at the cold and hot. Cold is -40 and hot is 125. So that is the environment setting. And set up the output directory. So you need some kind of space uh, to dump your output. Okay. And this is how a netlist file looks like. So if I could explain here, so it converts the amplifier into a number of lines. This is the simple op amp. And if you could see here, this will have all the connections, Q7, net6 meaning it is connected between the NPN transistor and the VCC. So this is how it background and the background it does netlist. Okay, so yeah, next we'll go to the LT Spice demo. Maybe I'll give you. Let me share my complete screen so that I'll start from where to download stuff and all. Okay, so here, okay, so if you go to Google, it is a freeware how to download LT Spice. You can go to, you can just search LT Spice, go to download. So it will take you to the analog devices. Analog devices is the company providing this LT Spice free tool. So you can download it for your Windows or whatever version, LT Spice for 11 end of support. So maybe you can download this newer version. So you can just directly go there and do it. So It does not require any prerequisites. So if you download, it will just go and sit in your space. So if you open the tool, it will looks like this. Okay. So now we want the model file. This is just a tool, right? So we want the model file. So what the professors in IIT has done, they have developed a LT Spice model for their students to do some kind of activity or assignments. So they have developed a foundry. So let me share you that also. If you go to this location, this link. So if you go here, Nagendra Krishnapura is a professor of IIT Madras, and he has uploaded all the model files. So as I mentioned, it is a TSMC 350 nanometer process, and this is TSMC 2250 nanometer and 180 and 130. Okay, till 180 we have for TSMC. These are all uh, these are all IBM, and these are all 45, 16 nanometer are predictive models. This is not from the foundry, but this will closely match to the foundry. So here we have to, so there is a procedure. So I can share you the link after this call. Maybe you can, it is clearly mentioned uh, how to install copy paste and how to install those models and how to install those CMOS, that NMOS and PMOS here. So it will give you a clear idea. Okay, this is it. So once you do all these steps, so you have this kind of tool. So now let me start with the basic circuit where is RC. So let me do it here. Okay. So here, what you can do, you can have a resistor. Okay, here is a resistor, and here is a capacitor, and we have a ground. This is the wire. So we connect R and C, and we have a source. Right? Okay, here we find the source voltage. Okay, this is a DC. So we want, I think this is the source. So I'm not much used to this tool, but anyway, I just wanted to, even I'm exploring this tool a lot, but basics I can provide. So here you go to advanced, so it is a sine wave. So let's assume we have an amplitude of say 100 milliwatt, and the frequency is let's say 1 meg. That's it. Okay, so now we have an RC. Our resistance is, let's assume, um, 1K, and the capacitor is say 500 femto. Okay. So now you have given all the things. Now you need to provide. Uh, so we can label nets also here, like V out, V out here, V out. Now, first, okay. Look, I need to also take a look at this page. I have to include that. I have to include TCC. So for each simulation, you need to include this model file. Uh, okay, here. And we need to define the simulation, what kind of simulation we are going to do. So for that, you need to include this price analysis. Right? So here, if you go, we want to run the transient analysis. So we are given 1 meg as a input sine wave. So it if you want to see is 10 cycles, we can give 10 microseconds. That will give you this. So now we are ready to go run. So the simulation is completed. Now if you check the V in, okay, if there is something, maybe here we need to provide the correct value, 100, whether it is a small m or bigger m. Maybe, let me try this 1 meg. Yeah, maybe the convention where what we provide differs. So so if you, the blue one is the input output, and the green one is the how to split it. So this is a V out, this is the V in. So let me see whether I can split it. So you can zoom in how the waveform looks like. So here, what you can do, you can plot the V. Okay, so you have now two. So now you can analyze here. So this is a low pass filter. So the filter frequency is uh, if you want to check the filter frequency, you can do an AC analysis. So how you do it is noise analysis. Go to AC analysis and see type usually decade. And start frequency is 1 hertz to let's say 1. Uh, so you can run this, save it, and you want to run this AC amplitude, we need to provide one. So this is the AC plot. So what you observe from it is, so it has a 3 dB bandwidth of 100 megahertz. So I have given an input as 1 megahertz, the sine wave. So it works properly. So let's try with let's say more than 100. That's 200, 300, 400, 400, 500 megahertz sine wave. Let's see what is happening. So I'm just showing you that the tool works properly. Okay. Okay, the triangle. Triangle. So now you will be able to see. Okay, now I don't see any change here. 100 meg. So this is 5 meg. Oh, again 5 meg. Right? So I want to give 500 meg, which is 500 meg. Okay, now you will be able to see. Okay, so what you observe from here is this is a low pass filter. So it can allow the frequency up to 100 megahertz. Now I have given a signal input of 500 megahertz. So if you see here, it is diminishing. Right? It is not passing the exact thing. So the gain of that is being reduced because of this RC filtering. So this is a very basic starting circuit where you can implement and see what is the frequency, and we can calculate this also, right? One over two pi root RC. So that will give you bandwidth of the circuit. So let me pause here. If you have any doubts or any discussion, let me pause here in this basic start basic circuit. Is there any questions you want to discuss in this tool on this
Yes,
basic?
sir. Yes, sir. I have one doubt, sir. Sir, basically, we have to follow the uh,
Okay, I
analog.
understood now. Maybe I'll go to a little more next level of circuit is a common source amplifier design.
Yes,
So
sir.
how we can do it? So here we go to instantiate and CMOS N. So this CMOS N is the instant from the processor. That link. When you install the LT Spice, you don't have the CMOS N. So you need to follow those steps, and the models will be dumped in, and you copy and you follow those steps. It will be done. I mean, it is very easy steps. So this is from the professor. So I have taken this uh, Mosian here, and I put a resistor. Let me show you how a common source amplifier, how to design with this one. Ground. Voltage. So this tool is very uh, intuitive to use. Yes. And then we need to connect a voltage source here. So this is the amplifier circuit. So here it is a passive RC filter. It does not have any gain. So here we want to develop a system where we want to have some gain. So this is the supply voltage we need to provide. Okay, this is your V out. Um, V out. And this let me name this as a VN. So now we'll assume some 1.8 volts as an input, and this is going to be sine wave, right? Where we want to check here DC offset. Let's assume we can keep 600 millivolt, and the amplitude is say uh, let's go with the smaller number 2 millivolt, and the frequency is say 100 kilohertz or 1 kilohertz. Yeah. And amplitude. For now, we want to check the bandwidth of this and gain and bandwidth. So let's assume I give me AC1 now. So we want to run this. Just put dot here and put a semicolon so that you are not running the transient. So here we want to see, okay, R is 1K and the width length is assumed 200 nano and width is 1 micro. So now we are going to save it and run the AC analysis. Okay, so now we get the plot. So here is minus because so this takes a lot of iteration to fix this. So please bear with me. This is how design is been done. So if you see now we have a gain of 7 dB, right? So we can increase this a little more, then we get the DC point. Yeah, now the gain is 12. I think it is better now. Over 30. Okay, so let's assume 15 dB gain. Okay, so we have a gain and the bandwidth is 100 megahertz for this circuit. So now this is a AC simulation. We check how far this can go, but in the transient, we are going to check in the transient. So we'll unblock this and transient. Stop trans. Now trans. So what is V in? Because we have given 100 kilohertz, right? So we need to run a little more longer. Yeah, maybe we can give the same 100 megahertz also, 1 meg. So this is your V in now. Okay, the red color one is a V in. So which has a amplitude of 2 millivolt. Okay, now let me plot the V out. So this is your V out, the green color one. So now if you see, um, it has a gain, right? It's 2 millivolt, and here the peak to peak become 256, 230, and 256. It is almost peak to peak is assume 25 millivolts. Okay, so you are giving a 2 millivolt input signal, and you are getting output of 25 millivolt. So which is a gain, right? It is a 15 dB whatever we achieved. So this is how a common. This is called a single stage common source amplifier. So this is a very useful tool here where we can do all other circuits also. We can have, I think, inductors will also be there. If you want to, if you have some idea and if you want to try implement, this tool is quite good. So you have an inductors also. So if you want to do some kind of simulation and you want to know how the output looks like, so you can use this tool. So this is a very handy tool. So I think I could stop with this circuit because you can have a lot of other circuits also you could try in the background. So I would like to stop here for this tool workshop. So I open for a discussion.
Sir, the output is should be you shown here is an inverter, sir.
So let me stop the presenting.
Yes, sir.
So please let me know if you have any questions or anything about the tool.
I have one doubt, sir. Are you hearing me, sir?
Hello.
I have one doubt, sir.
Yeah, please go ahead.
Yeah, sir. Because PSpace is the tool for analog IC design and other kind of verification of operating point like that, sir.
Okay.
What are the other types of software we have, open software like that? Already you have told that LT Space is one of the open source software like that, sir.
Yes.
Uh, if we connect with the other type of circuits, what kind of procedure we have to follow? So because I already done the PSpace, sir. There is some input issues I have faced, sir.
Okay.
So what kind of procedure we have to follow for a values given or how the circuit will be like a good output design like this.
I still sorry, I couldn't get your question. So
You have given the values in the size like that 1 kilohertz nano
yeah,
like
yeah,
that.
yeah, yeah, yeah,
Uh,
yeah. Okay.
for other circuit, what should be the design of input values we have to give us for an oscillator or an amplifier?
So that depends on the circuit. For this circuit, I have given some DC value because
Yes, sir.
yeah, this DC values and some kind of frequencies based on the I have done multiple circuits. So I know the what is the VT of this MOSFET. So
Yes,
I
sir.
have
Yes,
given based on that we need to have VGS more than VT. So 500 is a VT, and I have given 600 millivolt as a VT.
sir.
VGS. So similarly, it depends on the circuit. We need to analyze how the what is the requirement of the circuit. So 1 kilo ohms I've given based on okay If we give certain values, it will set in that value. So earlier, if you see, my output DC was close to 1.7 volts.
Yes,
Uh,
sir.
so we should be able to know where we need to reduce that voltage to make the uh, op amp to work. So that is why I increase the resistor to bring it down. So these are all intuitive method we need to implement in the
Yes,
circuit
yes,
design.
yes, sir. Is it any specialized material or a book be followed for it, sir, for a proper step-by-step procedure for this circuit to know the how to use the LT space like that, sir?
LT space is again a tool. So we
Yes, sir.
need to know what kind of values we have to give. So for that, we need to go through some kind of books like Razavi. They will provide you how to design. That will give you some analog basics. So
Name of the book, sir?
Razavi is
Asavi.
analog integrated circuit design. Razavi
Okay, sir.
and Gray and Mayer is their analog analysis and design of analog integrated circuits. So there are
Can
multiple books, but they may not give you the exact number what you need to give, but we need to understand from those books and we need to implement.
yes, sir.
Yeah.
Can you type in the chat box or because a lot of time I have the doubt in the design itself, sir. Because I am strong in digital, but while taking EC1 or EC2 like the electronics analog circuits, I have the problem in designing the simulation part, sir. That's why I asked, sir.
Okay, let me maybe post you that unlock. I
That's
can
a fine
post
loan.
you. Sorry.
That's a fine loan, sir. What are the book's name, sir? Name and
Yeah, yeah.
author.
So let me post you that
Yes, sir.
in the chat itself.
So, that's the thing about myself. Thank you, sir.
Sure. So this book, this design of analog CMOS integrated circuit, is a basic start for. So this is textbook for most of the universities for master degree students.
Yes, sir.
So this will cover almost the basic circuit design.
Yes, sir.
Yeah, this book.
Thank you, sir.
Sure. Any other questions?
Yes, if there are any questions, it can be raised.
Okay, if not, maybe we can
Yes, yes, sir.
yeah, call the
Yes, sir.
meeting.
Thank you, sir. On behalf of ECE Department, Sykatiya KJ College of Engineering, I take this opportunity to propose vote of thanks. I thank our resource person, Mr. J. Karthik Gopal. You are enlightened with your presence and knowledge, sir. We thank our management, principal sir, and HOD ma'am for their support with this. Now we move to the end of this session. Next session will be start shortly on tomorrow morning at 10 a.m. Thank you all.
Thank you, everyone, for the time. Thank you.
Thank you.
Bye.